So hi everyone, my name's Sam Vaughan. I'm a postdoc at the University of Sydney, and today I'm going to speak to you about galaxy mass, size and stellar metallicity in the SAMI survey. It's a paper which has been submitted for team review, but I've made some changes since that, so there should be something new for everybody. Cool, so starting at the beginning, a key thing in astronomy is that galaxies are made of stars. As Amelia mentioned, and as I think many of us are familiar with, stars create heavy elements throughout their lives, and astronomers call these metals. Since we know that the light from a galaxy is just the sum of the light from all its stars, ignoring gas emission lines for now, by measuring the light from a galaxy, we can use our knowledge of stellar evolution in order to infer things about the star formation history of a galaxy and the kind of processes which a galaxy has gone through during its lifetime. How do we do this? Well, luckily, we can decompose a galaxy spectrum to measure its metal content. So here's an example figure with the data in black. In red is a model galaxy spectrum, which we've made to try and best match the observed data. And we can then read off the metallicity from our best fit. This has been done for decades and decades, but something which is been much more popular recently in the past few decades is seeing how metallicity varies within a single galaxy. So here is one example galaxy from the SAMI survey. The y-axis shows the metallicity, and this is a log quantity. So a metallicity of 0 means your spectrum or your star has the same metallicity as our sun. Positive values are then more metal rich than our sun, and negative values are less metal rich than our sun. And the x-axis here is the radius within a galaxy. And so for this example, we can see that the center of this galaxy is the most metal rich, and then it becomes less and less towards the outskirts. So a quick aside, error bars are hard and team review is great. So how do we measure the error bars for one of our fits? The best thing to do is to take our best fit template and then add random noise and try measuring doing the same process again, seeing what result we get, and doing this lots of times to try and understand how our measurement varies with random noise in our spectrum. So for the SAMI survey, we have about 2,000 galaxies, which ends up with 70,000 different spectra, because of course each galaxy can have measurements from different parts of the same galaxy. And so I selected a subsample of 10,000 spectra and did this bootstrapping, did this adding random noise process, and then I tried to predict the uncertainty from other things. So I said, okay, given that it's this metallicity and this single noise, can I predict what the uncertainty is? This is fine. This is, I think, the right thing to do. So this is a plot of the metallicity and the signal noise properties of all of my spectra. So there's 70,000 odd spectra in here. This is just a 2D histogram. So my mistake was to select a random selection of spectra for the things I was going to bootstrap. But that means that because there were a few low metallicity spectra, it turns out that I wasn't very good at predicting the uncertainty for these low metallicity spectra, because there's a smaller fraction of things which are down here compared to high metallicity things at kind of medium signal noise. And it's only through some comments from co-authors that led me down a rabbit hole to kind of realize this mistake and manage to fix it before anything got submitted. So that's really nice. What I've done is now select a different subsample of things to measure the errors for, and now it's much more uniform across the entire distribution of points. So yeah, thanks very much, co-authors there. So moving on to the kind of science results from this work, we can now look at how, having done this for all 2,000 odd galaxies, we can now look at how the metal content of these galaxies varies between galaxies. So if we take the panel on the left to begin with, what I'm showing here is the metallicity at the very center of the galaxy. So at R equals 0, and I'm plotting that against the stellar mass. And this plot has been made many times. This is a well-known result. What you can see is that the blue points, which correspond to star-forming galaxies, are always below things which are red, so those are the passive galaxies, and also things which are green valley galaxies, kind of intermediate things. And so at fixed mass, passive galaxies are more metal-rich than star-forming galaxies. And this is a known result, but it's nice that I recover it in my own SAMI data. And the kind of key result is this plot on the right. So I followed the example of specifically Tanya Baroni and some other Astro 3D members who, as Scott mentioned actually in his intro talk, studied how metallicity varies not only with a galaxy's mass, but also with its size. So here now I'm plotting the same thing on the y-axis, metallicity, against log stellar mass minus log r, log radius. So that's kind of log m1r. And what you can see, as Matthew Collis described, all the points kind of go and squish together. So now all the points seem to follow the same, kind of very similar, well, yeah, the same locus in these spaces. And there's a much smaller difference now between a passive galaxy and a star-forming galaxy at fixed log m1r. This is nice, but can we relate it to the galaxy's formation history or evolutionary history? You know, we want to learn things about how they quenched, for example. So to do this, I took a series of, I took the stellar mass functions that we observed between a redshift of 1 and 6, and also used the mass size relation that we've measured and extrapolated a bit to get up to redshift 6. And then I sampled things from them. So that's kind of my way of taking a galaxy, for example, giving it a stellar mass and giving it a size. And then based on this mass and this size, I can now assign it a metallicity because of the relationship I showed in the previous slide. So yeah, knowing a galaxy's mass and size, I can tell you its stellar metallicity. So based on their starting redshifts, I then evolve them forward in steps of 100 million years. And when I say evolve them forward, what I mean is I say that galaxies evolve along the mass-size relation. Star-forming galaxies sit on the star formation rate against mass relationship, sometimes called the main sequence. And so, for example, if we know its star formation rate, we know how much mass it's going to gain in a set amount of time. Based on the amount of mass it gains and the mass-size relation, we can see how much it's going to grow in size. And then based on these two quantities, I can tell you how much it's going to increase in metallicity in order to stay on the mass, size, and metallicity relation I showed. So it's kind of stepping these things forward, saying that everything evolves along the relationships they're based on, basically. So when I get to redshift 0, I take all these galaxies and I select a sample which kind of closely matches my own SAMI observations. So I choose these points so they have the same distribution of stellar mass and the same distribution of size. And I'm then going to see whether my metallicity kind of assumptions will match the observed points. So the last thing to take into account is quenching. This is the mass size plane of my actual observed semi-galaxies, only looking at the centrals here, not looking at satellites. Yeah, so for my simulated galaxies, they're going to move in something like this, some kind of direction in this mass size plane as they grow. And I've in the model, I've put in that when a galaxy crosses this black line, they have a 5% chance of probability of quenching on their next time step. So yeah, for each time step, we kind of draw around a number, see if it's greater than if it's less than 0.05, and if so, that galaxy becomes quenched, and quenched galaxies stop growing in mass and size and metallicity. Yeah, so yeah, cool. And so if we do that, we get some quite nice results actually. So the top panel shows my SAMI data, just looking at central and isolated galaxies, ignoring satellites. And again, the blue points are star forming and the red points are quenched. Going from left to right, we have the mass metallicity relation, the metallicity against log M1R relation, and also the mass size plane. And the bottom panel shows you what my simulated galaxies look like. So you can see that we actually nicely recover each one of these, the location of quenched galaxies in all of these three plots, just with this simple model, and with this model where quenching happens pretty much instantaneously. So on timescales of less than 100 million years.
Yeah, I have 1 minute.
Yep, no problem. Yep, and so I've played around quite a lot of exactly how this quenching takes place. It's kind of too much to go into in this talk, I'm afraid, but again, the co-authors will see a paper draft very soon. And so yeah, I will now leave up my conclusions. So I find that metallicity follows a tighter relationship with log M minus log R than just log M alone. And that extends work from Tanya Baroni. She looked at star forming and crescent galaxies individually. And so this work is the first time we've looked at those two things together. I get a good match to our observational data by building a simple model with very fast quenching. And then this last point is kind of more just a question, something I was thinking about the other day. In this model, galaxies all follow parallel tracks in mass and size and metallicity because they all move along these relations. And that means that the kind of scatter and the differences we see today are basically all from their initial halo conditions, or the initial properties I give them. Yeah, the initial properties I give them, and which I'm kind of tenuously linking to their halo properties in the real universe. So is it really just these initial conditions which set the diversity of galaxies we see today? We can have a chat about that. So yeah, thanks very much.
Awesome. Thank you, Sam. Katie Grusher asks, at the SAMI resolution, individual regions of different metallicity are probably being blended together. Do you have a quantification of how impactful this blending is on your results? And does it get worse at the lower metallicity region where uncertainty predictions are harder to constrain, as you said before?
Interesting, yeah. So the SAMI resolution things are totally not resolved. So the seeing is some fraction, sizable fraction of the galaxy size, and so we can't, for example, find, I can't distinguish between a young star forming region and not. So that's kind of just all averaged together, I guess. And yeah, exactly how that impacts my results, I'd have to think a bit more about. I haven't thought about that too much, but I guess there could be issues there if these regions are predominantly in certain regions of the galaxy. So yeah, I can have to think about that a little more, I think.
All right. There are more questions on the Slack. I'm going to ask the one from Adam. He has the question, the sequences that you evolve the galaxies along evolve themselves. So for example, normalization of the main sequence changes. Do you account for that?
Yes. Yeah. So I use, I'm going to forget the name. There's a 2014 paper, I think Spiegel et al., who studied various different parameterizations of the main sequence, and they have it evolving with redshift, and so I just use their kind of consensus relation there, and also the mass size relation. I include redshift evolution there as well.
Awesome, thank you.